Have you ever wondered how your wristwatches work? Or with the press of a button, what makes your lighter to spark, which ignites the flame in your kitchen gas stoves? Or when doctor prescribes you to undergo ultrasound, what is responsible for imaging, transmission, and receiving of the signal? Well, the answer to all these questions is piezoelectric materials. In year 1880, two brother scientists, Pierre Curie and Jacques Curie, discovered that some crystalline materials like quartz, tourmaline, sugar produces charges when mechanical stress is applied on it. This phenomena is known as piezoelectricity and the materials as piezoelectric materials. The voltage produced across its surface were directly proportional to applied stress. This electricity can be harvested by applying a circuit just like a small battery or a power source. After 1 year, in 1881, another scientist, Gabriel Lippmann, found that the converse of this is also true. That is, if a crystalline material are treated with some excitation voltage, it tends to change the shape. Now, let's understand why material possess this behavior. Well, there can be two reasons for this. One is the atomic structure of the material, and second is the distribution of the charges inside the material. Normally, all non-piezoelectric material possess a center of symmetry across its unit cell. But piezoelectric materials are special. They have a non-symmetrical crystalline structure. Take for example, the most abundant element on the earth crust, that is quartz or silicon dioxide, which is a piezoelectric material. Silicon dioxide has a covalent structure. Each silicon atom is covalently bonded with 4 oxygen atoms. For convenience, I have shown only 3 oxygen atoms. Due to difference in electronegativity between the chemical species, there is a partial negative charge in oxygen and partial positive charge in silicon atom, which produces a dipole moment, which is the multiplication of charges and the distance between the charges. In normal condition, the net dipole moment is 0, but when the mechanical stresses is applied over it, the distance between the charges increases or decreases, which eventually also changes the dipole moment. Hence, no more, it remains the same. This leads to the generation of positive and negative charges on different phases. Having understood about the basic and the working of piezoelectric materials, let's now talk about the applications of piezoelectric materials. Well, it can be broadly classified into sensing, actuation, and power sources. In sensing, it has been widely used in microphones, sensors for measuring pressure, force, strain, load, velocities, or sometimes crack detection in materials, etc. The first time it was used in World War I as a sonar detector in which alternating current was applied on a piezoelectric material which vibrates. So this was actually an application of actuators. Apart from that, today it is used in loudspeakers, in motors, and for some nano positioning systems like scanning electron microscope and atomic force microscope. It can be widely used for energy because the mechanical stresses, load and the force is enormous, whereas electrical energy is critical and limited. Thanks for watching. If you like this video, please share it, comment, like and subscribe. Thank you again.